All right, folks. So we've been talking about inverse functions. It is time now to do a Desmos video. So we're going to look at inverting a function, and we're going to study what that does to the function's graph. So we're going to use as our example this function, f of x equals the square root of x plus 1. Now I'm going to plot some points on this function. So one point on this function is 0, 1. That's a point on this function. So my point is showed up right there. I'm also going to have a point like, let's see. Oh, I just realized I can do this thing. Let's see if I can figure out how to do this thing. Table. 0, 1. Yeah, 0, 1. And I've got like 3, 2. And I've got 8, 3, right? So there's a few points that are actually on this graph. So if I am going to graph the inverse of this function, then what I'm going to have is just x's and y's swapping, right? So I can graph some points on the inverse of this, and I can do it by just swapping the x's and y's. So I'm going to make the inverse purple, like red and purple. So instead of having x is 0 and y is 1, my inverse function should have x is 1 and y is 0. So that point should be on the graph of the inverse. Then the next point, 3, 2, is going to swap around to come to 3. That should be on the graph. And the other point, the third point there, 8, 3, should swap and become 3, 8. That should be on the graph. So what we've got now is, looks like these 2 points, these 2 points, these 2 points, right? Swapping the x's and y's actually has a certain effect. When you swap the x and y coordinates of a point, it produces a reflection over a specific diagonal line, y equals x. So this diagonal line here, if you reflect over that line, which means basically draw a line perpendicular to it, and they go the same distance away on the other side, then you would get a point on the graph of the inverse. So how can I graph the inverse? Well, right now, up here, I defined f of x. So y equals f of x is this graph. Let's make it red again so that it agrees. Okay, so that graph right there is the same exact graph plotting through those points. If I want to draw, like if I want Desmos to give me the graph of f inverse, all I have to do is write x equals f of y. That's all you got to do. And let's make it purple. Purple. X equals f of y. So there it is. That is the graph of the inverse. Now, this Desmos doesn't solve it for me. The Desmos doesn't tell me like what the inverse function would be as an algebraic expression, but it graphs it for me, right? It graphs it right there, and you can see it is this reflection over the line y equals x. That's the way inverses are always related to each other. When you look at the graph of f and the graph of f inverse, they will always be reflections over that line. So just to really kind of solidify that idea, let's look at another example. Let's define our function f. Let's define our function f as like x cubed plus 2x plus 1. And then I can, if I do y equals f of x, I get that graph. But if I do x equals f of y, I get the other graph of f inverse. That graph y equals x, that straight line, I'm going to make it dotted for us. Then you can see, again, these are inverses of one another. They're reflections of one another over that line. And no matter what you make this, if you make it like plus 3, plus 4, plus 5, if you make it plus 1x or maybe like just plus 2 or whatever you do to this function, its inverse is a reflection. Okay, so let's go back to this example. The f of x was equal to the square root of x plus 1. I'm going to move over here to the whiteboard, pull out my pen, and let's see if we can figure out what the inverse is. Okay, and we're going to find an actual algebraic expression to tell us the inverse. So first I'm going to write y equals the square root of x plus 1. Then we're going to invert by swapping the x and the y. So x would equal the square root of y plus 1. Now let's solve it. The first thing I need to do to solve for y is square both sides. And that will cancel the squaring, right? We have a square root. This number inside here had better be a positive number. So I square this square and it cancels out the square root. So now I have y plus 1. So now the only thing I have left to do is subtract 1. X squared minus 1 equals y. So that means that f inverse of x must be x squared minus 1. And I got it. So now let's go ahead and graph that. Going back to Desmos. If I graph, I'll call it g of x. Okay, I'm just going to give it a different name, g of x. If I graph x squared minus 1, and let's make it purple, right? Or let's make it blue so you can see the difference. I don't get exactly what I was expecting, right? This was supposed to be the same as the purple graph that I got. That is the correct inverse. This is the graph of the inverse, right? But this is the graph of the function that I got by swapping the x and y and solving for y, right? So why are they different from one another? Well, they're only different in that the purple graph is like the right-hand side of that parabola, right? So they're only different in that the purple graph only actually includes positive x values and zero is allowed. But the negative numbers are all excluded. What's the reason for that? Well, it turns out the reason for that is that the original graph, the square root graph, right? This was just the positive square root. If I take the negative square root, then I get the opposite side of that parabola. So if you solve the x squared, if you solve like for x here, you have to do the square root and do the plus or the minus. We're only talking about the plus, right? We're not talking about the minus, just the plus. So that's why really we're only using the right hand side. And on Desmos, you can this is called a domain restriction. You can put this in parentheses and write x and then write some sort of inequality. In this case, we'd write x greater than or equal to 0. And that restricts it to just positive x values. And now that graph matches exactly the graph that we were expecting to get. So really, our answer over here should say, should have a domain restriction of specifically 0 to infinity. Just the non-negative numbers, okay? And that is to make sure that that it is a true inverse of this graph over here. So there's something going on here, and the thing that's going on is that turns out actually not all graphs, not all functions are really invertible. If we get rid of that domain restriction, go back to this. Let's just kind of get rid of these things and these things. Let's just look at that. If you look at that graph, g of x, if we try to find the inverse of that parabola, the entire thing, instead of writing y equals g of x, I'll write x equals g of y. Make that, let's make that red or orange, maybe. If I take this parabola and try to find the inverse of that parabola by swapping the x and the y, what I get is this parabola. It's certainly a reflection over the diagonal line, y equals x. But the problem with the orange graph here is that this one is not a function. It doesn't pass the vertical line test, right? And the reason for that is because the original graph, this function did not pass the horizontal line test. So think back to when we introduced functions. I introduced this idea called one-to-one. Turns out one-to-one functions are the only functions that are invertible. If you're not one-to-one, then you're not invertible. So our takeaway here from the final takeaway here, besides the thing about reflecting, is that not all functions have inverses. Only one-to-one functions are invertible. So they have to, the graph of the function has to satisfy the horizontal line test, in order for it to be a function that you can invert. So that squaring function, like a parabola, is a great example of a function that technically is not invertible. You can take a square root, but you get a plus or minus, right? You get two answers, which makes it not a function any longer. We're not supposed to get two outputs. We're supposed to get one. So yeah, that's I think pretty much all I wanted to say about that. Actually, no, there is one thing I wanted to say about this. Okay. So if we look back at our f and our f inverse. Okay, let's look back at this thing. Let's get rid of that diagonal line. Okay, so if we look at what we have here, and I'm going to go ahead and maybe do this and this. In this graph right here, the f is in red. Okay, f is red, and f inverse is purple over here. If we look at the domain of f, that's going to be the set of all x coordinates. So imagine projecting this red graph down onto the x-axis. It go from -1 out to infinity, right? So it's going to be -1 to infinity. That's our domain of f. The range of f is the set of y coordinates. So the smallest y value on this f graph is the 0 right here, and then it goes up, right? And this goes up forever over here. As this goes out, it goes up and up and up forever. So the range is from 0 to infinity. Now, if we look at f inverse, the domain of f inverse is the x value for this graph, starting at 0 and going out to infinity, 0 to infinity. And the range of f inverse, with the y values, starting down here at -1 and going up to infinity, -1 to infinity. So when you look at the graph, or when you look at a function f and its inverse, I mean, you can see it from the graphs, but also when you look at the domain and range, you'll see they are just swapped. This is another thing that you'll always find with functions that are invertible. Is that when you look at the inverse, domain and range simply swap. They simply swap places. So that is a nice, simple, easy rule that you can use to help you figure out domains and ranges of inverse functions. That's all I wanted to say. I'll stop this video.